Okay, good afternoon. So my talk is going to be about enhancing live migration process for VM running large enterprise application, basically VM that are under heavy CPU and memory load. This work has been done in collaboration with Aidan Schrimman in Israel from SAP, which is kind enough to take our code and make it production ready and trying to push patch to KVM and Peter Svart from Umeå University in Norway. So the agenda of this talk is going to be about the background, what makes enterprise application special, or I would say very large VM special in live migration, and the different techniques we actually look into and how we can actually optimize and make live migration a viable solution for this type of virtual machines. So the background, migrating enterprise class application and what are the main issues. First of all, they tend to be bigger than average resource requirement. I would say that a VM with 16 gig of RAM and 32 gig of swap is more than common. Why it's like that? It means that most of like an ERP, for example, is running a lot of workflow, business process, and that kind of thing. And it's a very long-lived process. And it doesn't need to be, everything doesn't need to be in memory, but the thing is you need to have reference, you need to have trigger and timers, and it's most of the time linked to human interaction or real-life interaction. It doesn't mean it's actually going to be like the CPU is going to churn. It's going to require interaction from human. They tend to be slow. And so that's why you require a lot of memory to actually maintain all the different state of what's happening within your company. And it means that you're going to have like thousands of business process running at the same time. Literally in certain company, every single employee is represented by a business process. And some data structure need to be maintained in memory. And that's why you have a lot of memory and swap in the background to kind of help ease the load. These systems also are extremely sensitive to time variation. That's why in the beginning, when you started in beginning with virtualization, when you were getting time jitter and that kind of thing, systems were like extremely unstable, and they rely heavily on precise scheduling, triggers, timers. If you think about it, and you're running an ERP, and this system is linked to the credit card checking and that kind of thing. If an operation doesn't finish within a certain time, you need to roll back. And if, by example, this operation starts to get some delay and some suddenly the times jump because your VM has been frozen, the system might just say, hey, I cannot trust it anymore. And I might just shut down the system or just simply crash and say you need to restart from scratch. So the challenge when migrating such application is the first one is disconnection of service. As mentioned, gigabit Ethernet, the cutoff point is 5 seconds, and which represents approximately, if you're lucky, 500 megabytes of memory left and in the stop and copy phase. The thing is, if you're talking about 16 gigabytes of memory and a 32 gig of swap, that's very easily reached. And the downtime is extremely workload dependent. It really depends on how you're actually going to the access pattern in memory and that kind of thing. Problem is with business process and ERP type, the access pattern of memory is kind of extremely sparse. So you're touching a lot of page and doing very small change. And that kind of pattern is quite common with enterprise application. Another thing is disruption of service. Migration, especially in the iterative process in the beginning, in the pre-copy phase, tend to slowly try to migrate the system faster and faster to cope with the dirtying rate of the page. Problem is you kind of taking away resource from the VMs that are running within the machine, and you're kind of starving it. And you gradually degrade the performance of the running VMs, and in sometimes that can directly impact the system in such a way that you start dropping connection, or certain user just hang up and that kind of thing. As a result, it's very difficult to maintain consistency and transparency. And it's kind of rigid. It's very hard for us to predict how much time it will take to migrate a VM and if it actually will succeed. In the beginning, when we started looking into that like 3 years ago, we were discussing with our sysadmin, and he was just telling us, yeah, we tried live migration, and it was actually faster to shut down the system and restart it on other machines than actually migrating it. And it was actually safer at the same time. Another thing is, last Sunday at the dinner, somebody asked me, but why don't you just redesign your system so it's actually more like friendly, user-friendly for virtualization and that kind of thing? And my answer was like, yes and no. We can do it. But the problem is our customers tend to be extremely risk-averse. They don't want to have a system that changes quite often. Also, when they're buying that type of software, they're going to use it for the next 15 years on average. So it means that even next year, we spend a couple of billion and redesign everything like working perfectly. People who are buying software now, they're going to use it for the next 15 years. So you're going to have a lot of people that are still facing that type of problem. And I kind of lead us to trying to look into live migration and how we can ease the pain in a certain way.
Excuse me, can I interrupt you?
Yes.
So I want to understand the motivation a little bit more better then. If you're using this kind of heavy load application, is it realistic to the customers want to have some kind of heavy load situation to be really migrated to a different?
It doesn't really require to be heavy load. Most of the time, actually, if you have 20–30% load on your system, there's a good chance that the system won't actually migrate. It actually migrate, and then when it actually resume on the other side, it will actually fail because a trigger might have missed, and suddenly the system just say, I cannot trust it anymore, and I need to roll back certain parts, and for some reason just say, okay, I'm panicking, I'm going to crash because the thing is actually messed up. So the thing, it doesn't require a heavy load. The problem is it's touching a lot of the page at the same time because you have many different users connected to the same thing, and the interaction with the system is humanly bound, so it's a couple of seconds and stuff like that. So that's that kind of aspects. So first thing we look into was warm up for live migration. That was 3 years. The idea was just looking into how can we ease the live migration pressure, and also for us to learn what was actually happening within the live migration system. And the idea was extremely simple. It was just, can we extend the pre-copy phase and change it in such ways that we can dynamically adapt the bandwidth allocation rate through either manual or not a semi-automatic system, and so we can actually look at how much memory has already been transferred, what is working set left, and if we can decide when we actually want to switch to the full live migration, when we have the iterative process, and which is slightly more aggressive, and in order to kind of shorten the stop and copy phase. So that was kind of rather, I would say, naive, but the whole idea was to actually prove it was possible to do live migration at that point. And thing is, we got some quite okay results. The thing is, we started adding warm-up, and we extended basically the pre-copy phase. We actually just added some monitoring tools, and we were able to reduce the perceived downtime significantly. The rule of thumb is basically, with an ERP system, if your downtime is superior to 0.5 seconds, you have a good chance that your system is not going to be in perfect state at the other side. So that's with just 4 gigabytes and only 80% load and running the sales and distribution benchmark. So what we did next is, with the warm-up, we were like, that's fine, but it requires too much effort. The thing is, should be automatic. We should actually really focus on how can we improve the core of the live migration system. And we looked into how the page were touched and that kind of thing, and realized that a lot of pages were resent many times, like 5, 6, 7, 10 times within the live migration process. So we looked into how can we limit the impact of resending page. The idea was to use delta compression, which is, in certain way, quite simple. Rather than sending the whole page every time, was to can we just send a change? So what we did is we just introduced a cache, and we cached the page with the highest dirtying rate during the send operation. And when the page is sent, we just check if it's already in the cache. We have the previous copy, and if it's in the cache, we do a simple XOR between the two pages, and we do a binary run length encoding. The thing is, doing that, the overall time it's actually sent the delta is much shorter than the overall transfer. The problem is that algorithm is extremely dependent of the performance of the cache and the performance of the compression algorithm. And if you have many cache and that kind of thing, you kind of can have negative impact. But we went ahead and implemented it, and we did some benchmark. So the first one for testing, it's like memory-wide benchmark with 1 GB of RAM, 1 vCPU, and I think the working set for the LM bench was like between 700 megs, something like that. So it's near ideal case, high dirtying rate and that kind of thing. And the downtime is reduced by a factor of 100%, literally. And the throughput is increased by 63%. So it's actually quite good. The result was quite impressive the first time we tried it. Then we tried it with transcoded HD video. So same thing, 1 GB of RAM, 1 vCPU, real world. It's non-ideal case for testing the thing. And the UDP downtime was reduced from 8 seconds to 1, which means actually the amount of time we don't get any UDP transfer. And the migration is transparent, which means we don't have interruption in the video stream. Basically, when you watch it on the screen, you don't see any pause or anything. The migration is 31% faster, and 51% less data is actually sent over the wire to do the transfer. However, it's actually extremely dependent of your system. And you see with the memory benchmark, we actually, the migration time is slightly higher than the normal live migration. But the key thing is the downtime is actually almost non-existent. So then we decided to ramp up the difficulty a little bit. So we went for 8 GB of RAM VM with 4 vCPU, which is kind of the standard deployment, small deployment, with an SAP ERP, and we put 100% load because we decided to be adventurous. The thing is, if we use a vanilla algorithm, never worked. Actually, it crashed every single time. The thing also is, we saw that the impact in terms of CPU usage and also especially memory bandwidth usage with the vanilla one was literally starving the ERP benchmark. You have to think that when you do a benchmark, you have one machine running that you're trying to live transfer, and you have another machine that is actually doing query, simulating user and that kind of thing, and using bandwidth. And the starvation literally means that it was almost completely unusable. As you can see, the CPU usage dropped completely because people couldn't hit or do any query. Naturally, if you actually use different Ethernet device and that kind of thing on the side just to dedicate for live migration, that's fine. And then what actually is the thing? When we use the delta compression, we actually achieved to do a complete live migration without stopping, without anything, and a minimal impact in performance. I would say the performance of the ERP system dropped by 20–30% while doing the live migration. And a downtime was 0.2 seconds versus 2 seconds with the vanilla one. So we're quite happy with that, and we decided to look into how can we actually make that thing again better. So we looked into page prioritization. So it's reordering the page in a certain order. So it's kind of it's the same idea as what the Xen people did with the writable working set concept. It's basically saying, let's try to send the page that are going to be dirtied less first, and the ones that are being dirtied more last. So it's basically taking the famous dirty bitmap and trying to extend it a little bit to include priority. And as we're actually doing the live migration, we monitor the dirtying rate of the different page, and we change our priority. So it's basically, if you actually do a normal transfer with a vanilla algorithm, you get certain pages that are being sent quite often and another one less often, while if you actually prioritized it and keep monitoring it, the objective is actually to get all the pages that are dirtied less first, and then the one that are dirtied a lot last, which most of the time end up being stuck in a stop and copy phase. So with the streaming HD video migration, same setup as the previous slide. The vanilla algorithm, the total migration time is 22.1 seconds, and we transfer 5 megabytes of data, while for the priority algorithm, we drop to 15.4 seconds, and it's 225 megabytes. It's 31% faster, and 51% less data sent. If you look at that number, it's kind of quite similar to the one as delta compression. So we decided to do a comparison. And what it revealed is cache miss and compression efficiency issue was a big thing with the delta compression. If you look at the bottom right graphic, we tried with the vanilla and LM benchmark, and then we run the delta compression, the priority compression, and you can see that downtime is almost the same one as the one with delta compression, while the vanilla one just shoot up for the roof in terms of seconds. And when you look at the numbers, the amount of data transmitted and the migration downtime is always better with the priority algorithm. And what we wanted to understand is why. That didn't really make complete sense. And when actually we looked at the number of resend, the priority algorithm was doing a much better job limiting the number of resend. And as a result, the overall number of data sent over and over and over again. And the cache miss and the performance of the compression algorithm wasn't that good to actually compete with the priority algorithm. So Aidan started to look into that and say, can we, first of all, merge both technique? Can we use priority and delta compression? So first, he started looking into the delta compression, and one thing he realized very quickly is when we were doing the binary run length encoding, we were running it over the complete XOR page. While it means that basically we were doing it even on the 1 bit, which means actually the bits were changed. And that was a complete waste of time. The compression was completely inefficient with that. And it just tried to, let's try to just strip down the page and compress only the 0. And literally stripping down the part of the page that didn't change and leave the rest unchanged. The only way we could have compressed the one would have been to use a Bureau-Wheeler transform, but that was adding too much CPU usage and kind of thing. And for encoding page diff with this new version of the delta compression algorithm called XBZRLE for zero run length encoding, we get 20% more efficient than the XBRLE. But we're still 20% less efficient than LZO on Snappy. However, the speed, we are between 2.5 and 5 times more faster than the XOR plus LZO, and between 9 to 11 times faster than the original XBRLE. But we still have a problem with the cache miss. We didn't look into that yet. So we did performance comparison between all the different algorithms. What we did is we created a synthetic benchmark where we had a system that was actually dirtying page in a sparse, medium, and dense, and very dense manner. And we compared that with all the different algorithms. And it turned out the XBZRLE provides the best performance while also providing the lowest CPU usage in terms of compression time. It takes like 0.1 or 18th second to compress the overall data set while achieving like 2 gigabytes per second compression ratio. So actually that thing turned out to be extremely good. And then, so we decided to test it with a real-life benchmark. And what happened is XBZRNA typically use 50% of the CPU on our setup. It was a Core 2 Duo, not one of the big machines, and I think it was only 2 or 3 gig of RAM. While vanilla, that variation between 30 and 60%, but the main thing is XBZRNA for the same working set terminated within like 9-10 seconds, while the vanilla wasn't able to complete within the same allocated time. We actually stopped after 30 seconds because we're like the difference was so huge, like we actually stopped. And that's what ADAN is currently pushing within the QEMU code. This thing is not actually meant to be turned on all the time, but that might be an option at some point if people think it's actually quite useful. And one of the things we're actually looking into and in future work is actually merging the priority algorithm and the XBZRLE, so we can cache page with the highest dirtying rate, eliminate unnecessary cache check if they actually have the highest priority. Basically, they actually don't change that much. And eliminate page compression with low potential return. It means actually it changes so often that there's a good chance that the page has been changed so much that the compression ratio won't be good enough. And that's one of the things we're actually looking into. It's actually making the priority algorithm production ready and looking if we can actually merge both algorithms in such a way they can stack. And that's it. Any question?